Hello everyone, I'm Yukai from Tsinghua University. Today I'd like to introduce our work, a unified interactive model evaluation for classification, object detection, and instance segmentation in computer vision. This is a joint work with Changjian, Fengyuan, Shilong, Weikai, Zhaowei, Jing, Hanspeter, and Shixia. In computer vision, model evaluation assesses model performance and helps identify the causes of poor performance. Many model evaluation methods are proposed. For example, confusion matrix can help analyze classification results. However, existing techniques like the confusion matrix primarily focus on classification tasks. Apart from classification, there are other tasks that are popularly used in real-world applications, such as object detection. Besides, there are scenarios where multiple tasks are considered simultaneously, such as classifying a medical image while locating the lesions. Existing techniques are not applicable to these tasks or multitask scenarios. Therefore, a unified model evaluation method for different tasks in computer vision is desired. From a review of previous studies and a survey with 151 computer vision experts, we identified two key challenges in developing such a method. First, predictions in different tasks can be discrete or continuous. To analyze these predictions in a single tool, we need to model them in a unified way. Second, experts not only evaluate the overall performance on the entire dataset, but are also interested in analyzing performance at different levels of detail, such as subsets and individual samples. Therefore, a multi-level exploration environment for efficient model evaluation is necessary. For model evaluation, many methods have been proposed. However, these methods cannot support a unified model evaluation in different tasks. To tackle these two problems, we first model both discrete and continuous predictions by unified probability distributions. Based on the unified distributions, we develop coordinated visualizations to provide a multi-level exploration environment for efficient model evaluation. Based on these methods, we develop Uni-Evaluator. Here is the system overview of Uni-Evaluator. Given data samples and model predictions with both discrete and continuous variables, the unified formulation module models them by a probability distribution. Based on the distribution, the visualization module provides three coordinated visualizations to explain model performance at different levels. The matrix-based visualization provides an overview of model performance. Candidate data subsets are extracted and presented in the table visualization. Users can select the samples of interest and explore them in the grid visualization. Before I explain the technical details, I will introduce the case studies to demonstrate how to use Uni-Evaluator for model evaluation. We conducted two case studies. One focuses on an object detection task on COCO dataset, and the other focuses on an instance segmentation task on IStat dataset. In the first case study, we found 4 issues on the model and also the annotations of the dataset. In the second case study, we identified 3 issues on the model. The MAP of models in both case studies was improved. Next, I will focus on the first one. In this case study, the primary concern of the experts is the MAP on the test samples. Thus, they chose to evaluate the model on the test samples. In the matrix-based visualization, each row of the matrix represents a ground truth class, and each column represents a predicted class. The cell color encodes the confusion between classes. Most of the off-diagonal cells have light colors. It indicates that the model classifies objects of different superclasses well. However, the MAP is still low. The expert thinks the model fails to localize objects accurately. As the localization performance concerns both the sizes and the shifting directions of the detected objects, the expert decides to evaluate the model from these two perspectives. Switch to the size mode. The pie chart in each cell summarizes the sizes of detected objects. Large green and yellow sectors indicate large errors in sizes. All the large pie charts with large size errors are on the diagonal of the matrix. Select the diagonal cell with the most size arrows, which is the silver class outdoor, and expand it to a submatrix. The diagonal cell of traffic light contributes the majority of the size arrows. However, the predictions on the associated objects do not show clear reasons for these size arrows. Turn to the table visualization to analyze the performance on different subsets in this cell. Sort the subsets by the recall scores in ascending order. Select the one with the lowest recall. Click the green sector in the matrix to examine the predictions with smaller sizes than ground truths. Most of these predictions exist in blurred images. Apply Gaussian noise data augmentation to generate blurred images in the training data and retrain the model. The AP of traffic light is increased. Then, examine the predictions with larger sizes. Predictions are precise, while some annotations are not. Re-annotate the bounding boxes of traffic light on test samples. The AP of traffic light is further increased. Switch to the direction mode. In each cell, the length of each arrow encodes the number of the objects shifted in that direction. The circle in the middle represents the predicted objects with precise positions. There are 4 cells with apparently long arrows in specific directions. Analyze cell A first. Expand this cell to a submatrix. The cell where a person is confused with skis contributes the majority of the direction arrows. Click the downward arrow to check the associated objects. The predicted skis are actually precisely localized, but the annotations of the corresponding skis are absent. Add the missing annotations of skis in the test samples. The expert conducted a post-analysis on the re-annotated test samples. First, he re-evaluated performance of a large pre-trained SOTA model, intern image, and got 2.3% of gain in MAP. This showed that the higher performance on large models was not due to overfitting annotation errors. Meanwhile, the expert noted that the current annotations might not be accurate enough for evaluation. He emphasized the importance of re-annotating the remaining 71 classes. On the other hand, the expert suspected the annotations of the training samples were also inaccurate. As the model predictions seemed more accurate in most cases, the expert tried to fine-tune a small model with the predictions from a larger model. The result turned out that performance of the small model was further increased. After demonstrating the case study, I want to explain the technical details. I will mainly focus on the unified formulation in our method. I will take object detection as an example to demonstrate the idea. Given images with ground truth and the model, we take the ground truth and the model predictions as input. What we try to do is to model the variables in ground truth and predictions by probability distributions. However, in this probabilistic framing, it is non-trivial to match each continuous prediction with the corresponding ground truth, due to multiple possible ground truth annotations. To tackle this issue, we develop an object matching algorithm. Mathematically, the matching between the predictions and ground truths can be modeled as a one-to-many assignment problem, which maximizes the total assignment award. Zij is a binary variable, indicating whether the ith ground truth is matched with the jth prediction. Aij is the award. It is defined as the weighted sum of 3 scores. Label consistency score encourages the matched prediction and ground truths have the same label. Position consistency score encourages the matched prediction and ground truths have a large overlap. Uniqueness score encourages the ground truth is matched with one prediction. By optimizing the total assignment award, we can obtain the matching results. Based on the matching between predictions and ground truths, we adopt the joint probability distribution to model both discrete and continuous variables. For discrete variables, the probability mass function is used to determine the probability of taking on a specific value. For continuous variables, the probability is calculated over intervals using the cumulative distribution function. With the two functions, The joint probability is calculated using the conditional probability. We illustrate the calculation of the joint probability using an object detection example. Suppose this person wants to analyze the detected objects with the ground truth label cat and prediction confidence larger than 0.5. He can fulfill his analysis by this formula, which can be further decomposed using conditional probability. The probabilistic framework enables users to process data using standard operations, including marginalization and conditioning. The marginalization operation discards variables in the distribution, allowing users to focus on analyzing the variables of interest. The conditioning operation constrains variables to be within specific intervals, which enables users to analyze the subsets of interest. To conclude our work, we present UniEvaluator, a visual analysis tool that supports a unified interactive model evaluation for computer vision tasks. 2 case studies are conducted to demonstrate the effectiveness of UniEvaluator in improving the model and the associated data in object detection and instance segmentation. In the future, there are several directions to follow. First, we plan to investigate how to support identifying problematic subsets based on semantic attributes in different computer vision tasks. Second, we plan to extend our system to support effective model comparison. Thanks for your attention. Our codes and demo are available on our project website. I'm happy to take any questions.